We're in the last 2 weeks, right? We're going to cover autocorrelation, spectral density, and we're going to cover linear regression.
A box insert spiral contains 4 40-watt light bulbs.
Hold it, 440 watt. I'm going to call that A. 5 watt.
60 watts.
60 watt, call that B.
And 675.
75 watt, call that C. Okay, go ahead.
Suppose that 3 bulbs are randomly selected. What is the probability that exactly 2 of the selected bulbs are rated at 75 watts?
With me? They want to know the probability that 2 are 75 watts given 3 selected. That's basically it. So first thing I'm going to do is, and I suggest you do, is look at the total number of bulbs. So here we got 15 bulbs, right? Now, if you select 3 of them, how do I figure out how many different combinations can happen? Notice I use the word combinations, not permutations. Combinations can happen if I select 3 from 15. So this would be the way to find 3 bulbs out of 15 total. This is without order. So this is going to be, this particular one is going to be n factorial over n minus k factorial, right? Kn, and here k is always less than or equal to n. And this is for combinations. So when I look at this and I want, this is just a simple number of ways I can take this. So P of 315 is going to be, we're taking 3 bulbs from 15 total, right? And it's a combination. So isn't this 15 factorial up top, right? And then it's going to be what? 3 factorial, and this is 15 minus 3 factorial, right? This is 12 factorial, so I got 15 times 14 times 13, and then it's times 12 factorial, so I can get rid of that. And then I have over 3 factorial, which is 3 times 2. 15 by 3 is 5, isn't it? 2 into 14 is 7.
I think you forgot the 13.
I think I did. So 5 times 7 times 13.
Yeah, that's 455.
What is it, 4 what?
55.
Now we're going to do this part, 2 75 watts, and the way I'm going to do that, first I take this, P of 315, that's the total number of combinations of any 3 bulbs you can take, where order is not important. Now, when we take a look at, we're asking for 2 75 watt. So the 75 watt, we have 6 bulbs, and that's going to be, the way he orders it, it would be larger number on top, smaller on the bottom.
And this is a permutation?
Combination, that's combination. Remember, he wants 2. So here we're getting, how many ways do you take 2 bulbs and out of 6 total? Because that's what we got right here, right? Now you got you got 1 left. So I got 15 total bulbs. So 15 minus 6 right here, that's 9 total. So if I look at the way to take one of those bulbs from 9, this would be 9 over 1. The first one here is 6 factorial over 2 factorial, and then 6 minus 2 factorial. That's the first part. This part is 9 factorial, right? Over 1 factorial, which is 1, times 9 minus 1, which is 8 factorial, all over 15 factorial over 3 factorial, and this is 15 minus 3 factorial. I'll put the whole thing down there. Now, if you run the numbers on this, that's the first part. What's the second part?
What is the probability that all 3 of the selected bulbs have the same rating?
So you're still going to have this in the bottom, right? But now it's an additive process, because if you do the Venn diagram on that one, this is all bulbs, 15 bulbs. Here's A, that would be 7, or it could be, 40. B is 60, and C is going to be 75, and they're different numbers. It's still an aerial thing, but this is additive. The probability of selecting all that are the same, either all 40, 60, or 75, on the bottom, you're still going to have the combination. If you take 3, this is the total number of ways to take them, which is P of 3, 15. And up here, then it's going to be, and this should be 4, 3, plus, and this is going to be, do y'all agree with that, first of all? Because they're distinct, right?
Because they're distinct, you add them?
there's no overlap, like A can't be in C, C can't be in B and stuff like this. So if you look at this, we're talking about if we take 3 of these, that's there, right? If you think about it. 3 of these is here. 3 of these is here. The total area is that, but we take 3 of those. I'm trying to just give you a visual. So what do you get for that one when you do it? 0.0747? What's part C?
What is the probability that one bulb of each type is selected?
1 bulb of each type. So the total number is, the total combinations is still this guy, right? What was that number again? 455? 455, right? On the bottom. Now what do we do on top? It's the probability of 1 bulb of each type, right? Well, if you look at this, 1 bulb of this would be what? 4 over 1, right? And then 1 of the next, now these are multiplying, right? Because these probabilities, you can have 1 of each occur simultaneously, basically selecting them that way. And this is going to be 5-1 and 6-1. Do you agree with that? I don't know what that is. If you thought to yourself, well, if I select 1 bulb and it's this, one of the thoughts you should have, or at least I had, was, well, now there's not 15, there's 14. But the numbers of the remaining bulbs, the ratioing is still the same, even if you select, if you're assuming you're selecting this one, you didn't change the numbers of either of those two. That's the whole idea. So you don't have to do the n-1 thing.
Suppose now that bulbs are to be selected one by one until a 75 watt bulb is found. What is the probability that it is necessary to examine at least 6 bulbs?
The probability of selecting a 75 watt, the first, and this is one of these crazy things, it can or can't be selected, right? As you select one, the number goes down, all right? So the probability, first one of getting a 75 watt bulb, and we just have the number n equals 1, is simply going to be what? The number of 75 watt bulbs, which is, well, it is a combination, but you can do it with binomial coefficients if you want to do this one. All right, now, then probability here, that's 6/15, would be the probability of selecting the first one, right? Now it's assuming you didn't select it, right? So then the probability, because if you did, you're done. I think you can easily do it this way. So the probability of, and I'm going to put not selecting 75 watt bulb, that probability would be equal to, depending on the number you've taken, would be a summation here, and would be I in n attempts equal 1 to n. You can have the number of bulbs, which is 15, over I factorial. And this is going to be 15 minus I factorial. Then you have to have a probability of selecting a 75 watt bulb, which is, what is that, 6 over 15 to the I power times, and this is going to be 1 minus 9 over 15 to the, and this is going to be 15 minus I. And this is the probability of not selecting it. 1 minus this would be the probability of selecting it. He did what?
He did a combination of 9, 5 over 15 over 5. And the explanation says it is necessary to examine at least 6 bulbs if and only if the first 5 light bulbs were all of the 40 watt or 60 watt variety. Since there are 9 such bulbs, the chance of this event is 9 over 5 over 15.
Yeah, but he's doing the not business. He's basically saying if it is not, and that's what this is going to end up being, because I got 6 over 15 here and 9 over 15 here. Wait a second. This should be 15 minus I, and this should be I. I'm bad about that, sorry. Right. He wants the probability of not selecting until the 6th attempt. Then he's right. Well, I think I know. What he did is he assumed you've got 9 bulbs, that are basically of the ones that are on 75 watt. So if he took 9 over 5, and he's going to have that in the combination divided by the total number of combinations, which would be 15 over 5, then that would give you the probability of not selecting. That's what he's doing. Of not selecting up to that one. The answer he has for part D is probably right. is going to be equal to, since there's 9 bulbs that are not 75 watt, and he wants, he's selecting 5. So 9, 5, and then down here is going to be 15, 5. And these are the combinational values, right? Let me put up the formulas first in the corner so I can reference them. If we have a sample, the sample itself, the mean of the sample is just 1 over the number times the summation of, these are sample values from I equals 1 to n, and then expected value of the average value. And this is a random variable, is the actual mean value of the samples. And then the variance of that is going to be equal to x bar hat quantity squared, that minus x bar squared. After all is said and done, you're going to have the variance of this, which is sigma x bar hat squared, is given sigma squared divided by n. This is for a large number, and then sigma of x bar hat squared is equal to sigma squared over n, and then it's going to be multiplied by quantity capital N minus n, my bad, over n minus 1. And as n gets large, these two become the same. And this is for small population. N large. Then we can say the actual density function. He doesn't say this, but this is the implied value. Square root of 2 pi sigma x bar here, x bar hat, or the variance of the sample, or I'm sorry, standard deviation of sample. Just write this down because then you can use the tables of the actual normal distribution to get this. I didn't see this in his book. The reason I'm saying this, that's a normal distribution. And if you can assume it's a normal distribution, then you can find the probability. If you can find sigma x right here, which is the variance of the samples, or if you can, or the standard deviation of the sample, then if you know this, you can either use the Q function or that, whatever he calls that f of x function in the book, which your calculators have. In other words, this is a normally distributed variable. That's the idea if n is large. No, this isn't in the book, but he says normally distributed. That's this, and he shows the probability of like being from 0.99 to 1 point, after you normalize, 1.01.
Is that a X?
I call it x hat because this stuff has to do with
X bar hat.
Yeah, it's the variance of the samples or the standard deviation of the samples. So then if we have the sample variance, sigma squared is the sample variance. Then this is a bias estimator. The expected value of s squared is equal to n minus 1 over n sigma squared. And this is biased. And then the unbiased estimate is he puts a bar over it, squares it, and that's n over n minus 1 s squared. Well, if you look at the expected value of this times the expected value of this, you can see what happens. You get the expected value of s bar squared is equal to n over n minus 1, the expected value of s squared, and that's n minus 1 over n sigma squared. So you see these cancel, that cancels, and that's why it's called unbiased. I'm just showing you what he's talking about, because he just puts this down. He doesn't say, in fact, the expected value of this is sigma squared. That's the point. Variance of the unbiased estimate. This is crazy sometimes. The variance of s bar squared, and here's where it gets interesting, n over n minus 1, and he said that the proof is tedious, and then it's u to the 4th, this formula I know I used, sigma to the 4th, now this is important, u to the 4th is the 4th central moment, and then u to the 4th is the expected value of, and it'd be x minus x bar to the 4th power. Now, if the mean is 0, it is the mean, it's the expected value of x to the fourth, if the mean is 0. That's something important to say. I think that's all the formulas. By the way, I recommend you do the exercises in chapter 4 here, if I assign. Because the exercises don't give solutions, but they force you to think through it. The mean is 10 and the variance is 9. That's the true variance, true mean. And he asks some questions. And I'm going to just take and read a section of this. This is in the middle of section on page 164. To do this, the probability density function of the estimate must be known in the case of a large sample size. The central limit theorem comes to the rescue and assures us that since the estimated mean is related to the sum of a large number of independent random variables, the sum is very nearly Gaussian, regardless of the density function of the individual sample values. Thus, we can say the probability, and this is of the random variable x bar hat, is with 1% of x bar is, now this is the thing I was going to talk about, regarding 4.1. So this waveform 4.1 in figure 4-1 here, the actual value of sigma squared is 9, and the actual mean value is 10. The variance of x bar hat here is going to be 0.01, and he gets this from the formula right here. So he's going to, where this comes from is sigma of x bar hat equals sigma squared over n. And for a previous problem, this comes out to be, since they know sigma squared is 9, and the value of n that they give, this comes out to, this should be squared, 0.01, and that means sigma of x bar hat is equal to 0.1. And here's the problem. When you talk about something, normally when you talk about a variable, a random variable, if you talk about some random variable x, and it has an f of x, it's Gauss, it's 1 over square root of 2 pi sigma, and this would be for that random variable exp of x minus x bar squared over 2 sigma squared, and that's valid everywhere. Now, if you have a mean value that is a random variable, maybe I should put a capital X there. Now he says, I've got a mean value, so we're summing, and you know the mean value, the more you take, the more values you take in it, the closer it gets to the actual mean value. So this mean value, the larger the value, the actual smaller the variance is, has a variance, and that variance associated with the, and this is the random variables squared, is going to be given by that right there for large numbers, sigma squared, actual value over n. Now in the problem, the first part of the problem is how many values of n do you, or how many samples do you need to get this with a value of 0.01 or 1% of the actual standard deviation. That's the first part of the problem. Remember, this right here is the actual probability density function for the entire sample, all samples. Now we're talking about a subset here that's a random variable where you take n values. This value here, which is the mean value, is going to have a probability density function that is given in part by this right here. Now that's the mean value. By the way, the mean value, you don't need to subtract anything from it on this one. So this will have a density function, an f of x at bar of x, and that is a random variable. It's going to be 1 over the square root of 2 pi sigma of x hat. That's, again, random variable, random variable. Standard deviation of the mean of the samples, exp, and here it's going to be minus x bar hat squared over 2 sigma x bar hat squared. This is related to the mean value. The larger the number of samples, the closer this gets to the true mean. And the actual variance of this function gets smaller and smaller. So you might say this, and this is just for me, a thought experiment. If this is the true mean, whatever that is, if you have a small number of samples, true mean now here, Alright, and this is going to be values of x, but it's a random variable. So, well, I'll put true mean there, this is the x bar hat. So these are possible values of this sample mean. And this is f of x bar hat, the random variable x bar hat. Now, that's a small number of samples. As the number of samples gets larger and larger, it starts approaching just a single value, because then the actual variance will go to zero. The mean value of the number of samples will be the true mean. But this is what we're talking about. So this is the statistics of the theoretical sample mean for a certain number of samples. And you'll notice that sigma value is a function of n. Now this is a large number of samples. So then they say, so we assume if there's a large number of samples and we have a sample size that's more than a few of significance. Then he says, the middle page 164, of course, estimating the mean value of the random time function. Specific variance does not necessarily imply an estimate of the real, it's really within 1% of the true mean. It is possible, however, to determine the probability of estimate of the mean, in other words, of the sample is within 1% or any amount. And the way you're going to do it, if this is the density function there, to get the probability that the actual value of the mean that you calculate of the samples is within 1%, of the actual mean value, you're going to have to technically integrate this function right there. I'll just call it f of x bar hat of x bar hat dx bar hat. And here you're going to have to integrate it from 0.99, the mean value, to 1.01, the mean value that you have. So you're going to integrate that. And what he does say is, because now they use that cumulative function f, and he says what's going to be, remember when we have f of, the way he calls it is x, what we end up doing is saying this is going to be his cumulative distribution function from minus infinity to the point of observation. It's going to be of x minus the mean value over sigma. That's the way in the book, that's what he calls the f function. So here, and this is what your calculator should be able to do for you, right here. That means the probability is within 1%. It's going to be the integral, like I said there, but this is going to be the psi function of, and here you would take x bar hat minus x bar over, and this would be the variance though, so I better put down, this is going to be sigma of x bar hat minus phi of x bar hat. It actually should be plus here. And then it'd be x minus x bar over sigma. And that's going to be phi of, so if you're looking at 1% difference, that's going to be, he says the mean value is 10 in this one, and this value is given as 1% minus phi of 9.9 minus 10 over 0.1. But your calculators should be able to, and that comes down to 0.6826 according to him. Calculators, you have that. So NCDF, the lower limit is going to be 9.9. Upper limit is 10.1. The mean value would be 10 because that's given. And the standard deviation is 0.1. And that is the standard deviation of the sample. You got that? Okay, it works. That's what he's saying. The whole key to this thing is, remember, the mean value is given of the actual samples, all the samples. And here, you have to use the actual standard deviation of the variance of the samples. Variance of the samples, you just take a square root. But that's kind of an odd thing because, remember, for a large number of samples, this is the variance.
4-2.4.
Okay, go ahead.
A political poll is assessing the relative strengths of two presidential candidates. A value of +1, +1, is assigned to every person who states a preference for candidate A, and a value of -1 is assigned to anyone who indicates a preference for candidate B. Part A, find the sample mean if 60% of those polled indicate a preference for candidate A.
This is gonna be 0.6 times 1, right? Plus 0.4 times -1. And if you look at that, what is that? You got 0.2 should be the answer.
Write an expression for the sample mean as a function of the sample size and the percentage of those polled that are in favor of candidate A. Yeah, they want an expression for X bar caret, so the sample mean as a function of n, the sample size, and whatever we want to call the percentage of those polled that are in favor of candidate A.
It's gonna be n time, they want an expression for the mean value, and the mean value for a large number of samples is gonna go to 0.2. That we know. You sample one person, that should be the same. He gives you a 60%, 40% break, right? If you're sampling, that doesn't change. I mean, it's an infinite number of people, isn't it?
I mean, you can assume that. He just wants you to write an expression for for 0.2 basically. But now you're using two variables. You're using n, sample size, and some variable for
Capital N, you mean?
no,
Just small n.
yeah, small n.
Well, it's still gonna be a summation here of 1 over n, that would be the number, right? But this is very odd.
Yeah.
I'm sorry. This is gonna be I times 0.6. And then it's plus 1 minus I times 0.4. Hold it. I don't see how you can, hold on for a second. If he wants, for that mean value, every sample has the same possibility of either value. I mean, it has 60% chance of being A and a 40% chance of being B. So for each sample you select, the average value is 0.2, I mean, on average, right? What equation do you have, Bradley?
I think it's 2p%.
Yeah, 2p%, but p% is equal to A. 2p% and p% is equal to A.
So P is 0.6?
Minus
Yeah, it's just variables. It's just an
It's
expression.
just variable.
That's what I was saying. You can make your second variable whatever you wanted.
It's n times p% minus n times 1 minus
Let's move on, I'm not
p%.
sure about that one. Go ahead, what's the next one?
This is one I was confused on. Find the sample size necessary to estimate the percentage of persons in favor of candidate A with a standard deviation no greater than 0.1%.
That would be the variance. Now, if you look at that, what is that? That's sigma squared over n for the number, right? Does he give you a sigma value?
No.
That we can get. We got this, so what we need to get n is sigma squared. And here, I'll do it this way, so mean value on this one for 1 minus 1 is 0.2. If we want the mean squared value variance, so sigma of, and this is going to be of the samples, that's going to be of the samples minus x bar of the samples squared. X bar is 0.2 minus 0.2 squared. And this, the mean value of that, x squared bar, that's the summation probability. This is going to be 0.6 times 1 plus 0.4, and this is going to be minus 1 squared of 1. So that's going to be, looks like 1 here. This is going to be 0.96. So over here, let's see if we get this right. We got 1 over 1,000 equal to 0.96 over n. So n is n equal to 960 roughly? 10 to the 6. 0.1%.
I said 0.1%.
1% would be equal to 0.01.
Yeah.
0.1% would be equal to 0.001, right? That's 1 over 1,000. Squaring it, that's the problem. This should be squared.
That's the answer, yes, listen.
Yeah, it's approximately that.
See this? That should be 0. Times 96 here. but he doesn't have that,
What's 10 to the 9.6 times 10 to the negative 7?
That's it.
Approximately 10 to the 6th. Yeah.
all right, close to it. The quiz is gonna be related to exercise 421 and 422 in section 4-2. Go through problems 4-2.2 through 4-2.5. It'll be related to those problems, okay? In the sampling theory one, mean of the sample you should know. The expected value of the mean, which is the true mean, the variance of the sample. I'll tell you what, I'll give you the formulas, the sigma squared over n and sigma squared over n minus 1 over n minus 1. Because if you give me a population size and you say 60% of
Yeah,
this.
that was, it didn't give a population size. So it's like, well, is this small population? Is this large population?
I assume, if it's polling, you gotta assume it's infinite.